There are places on Earth where stone and silence speak the same language, where the border between China and the Democratic People's Republic of Korea meets at 2,700 meters above the sea. A mountain rises, not sharply, but with the patience of something very old. The Koreans call it Paektu. The Chinese know it as Changbishon, the ever-white mountain. Both names carry the weight of reverence. This is a volcano. But to call it merely that would be to miss the story entirely. For more than 1,000 years, Paektu has been woven into the fabric of Korean mythology and identity. It is considered the sacred birthplace of the Korean people, the mountain where Dangun, the legendary founder of the first Korean kingdom, descended from heaven. Pilgrims have climbed its slopes through snow and summer alike. Poets have written of its majesty in verses passed down through generations. Entire dynasties have looked upon it as the axis upon which heaven and earth meet. The mountain has witnessed empires rise and fall. It has watched kingdoms fracture and reunite. It has stood silent as armies marched past its foothills, as borders were drawn and redrawn across its very summit. But beneath the reverence, beneath the myth and the mist and the human stories told in its shadow, lies something far older than any memory we can hold. The earth remembers, and what it remembers about this mountain is extraordinary. In the year 946 of the Common Era, during a time when Europe was deep in its medieval darkness and the Song dynasty was rising in China, Mount Paektu awoke, not with a whisper, not with the kind of warning that anyone alive today could fully comprehend. It erupted with a force so immense that it would later be recognized by geologists as one of the largest volcanic events of the last 2,000 years. Scientists today call it the Millennium Eruption, a name that carries both precision and poetry. The skies darkened across entire regions. Ash fell like grey snow as far as northern Japan, 500 kilometers to the east, blanketing rice fields and fishing villages in a ghostly layer. The mountain expelled more than 100 cubic kilometers of rock, ash, and pumice into the atmosphere, enough material to bury entire cities. To put that into perspective, this single eruption released more energy than Krakatoa in 1883. Which killed tens of thousands. It was more violent than Mount St. Helens in 1980, which Americans still remember vividly. The Millennium Eruption reshaped not just the mountain, but the very climate of the Northern Hemisphere for years to come. Where once stood a towering volcanic peak perhaps 3,000 meters high or more, there now remains a vast caldera, a bowl 5 kilometers wide, carved by the mountain's own catastrophic collapse. The summit simply fell inward, swallowed by the emptiness left when magma drained from the chamber beneath. And within that bowl, fed by centuries of rain and snowmelt, fed by springs that rise from deep within the earth, lies Heaven Lake Chanji in Korean, Tianchi in Chinese. A body of water so deep it reaches nearly 400 meters in places. So cold that even in summer, its temperature barely rises above freezing near the bottom. So still on windless days that it seems to hold the mountain's memory within its crystalline depths. Local people say that dragons once lived in this lake, that spirits guard its shores, that to drink from its waters brings clarity and long life. Perhaps they are right, in their way. Perhaps every myth carries a kernel of truth. Perhaps what they sensed across generations was simply this, that the lake itself is a record, a liquid archive of something unimaginably powerful. But this story is not merely one of destruction. It is a story about time, about patience, about the forces that shape our world while we live our brief, flickering lives upon its surface. It is a story about a mountain that erupted with biblical fury more than a millennium ago and yet still breathes quietly beneath the lake. For Paektu is not finished. The earth never truly sleeps, it only rests. And what seems silent is often only waiting. This is a story shaped by time and patience. If you choose to remain with us, the earth is about to reveal one of its quiet transformations. To understand what happened at Mount Paektu in the year 946, we must first understand how the earth speaks. It does not speak in words, it speaks in tremors. In the slow grinding of tectonic plates, in the patient accumulation of pressure over centuries, over millennia, until something must give way. Mount Paektu sits upon one of the planet's great geological seams. Here, beneath the mountain, the Pacific Plate meets the Eurasian Plate in an ancient, ongoing collision. This is not a sudden crash. It is a slow-motion convergence that has been unfolding for millions of years, a continental embrace measured in centimeters per decade. As the Pacific Plate slides beneath the Eurasian Plate in a process geologists call subduction, it descends into the mantle. Down there, in that realm of unimaginable heat and pressure, rock behaves differently than we imagine. It flows, it melts, it becomes magma. And magma, like all things under pressure, seeks release. Beneath Paektu, over geological epochs, a massive chamber formed. A reservoir of molten rock, slowly filling like water behind a dam. The mountain above was merely the lid, the plug holding back forces that no human construction could withstand.
Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes.
For centuries before the Millennium Eruption, the mountain gave signs. Subtle signs. The kind that ancient peoples might have noticed but could not fully interpret. Small earthquakes rippled through the region. Hot springs began to bubble more vigorously. The temperature of streams descending from the mountain rose slightly. Animals behaved strangely, birds departing earlier than usual, livestock growing restless without apparent cause. These were the mountain's whispers, its vocabulary of warning. But in the year 946, the whispers became a roar. The eruption, when it came, unfolded in stages, each more catastrophic than the last. First came the Plinian phase, named after Plinian the Elder, who died observing Vesuvius in 79 AD. This is when a volcano sends a column of ash and gas vertically into the stratosphere, reaching heights of perhaps 40 kilometers or more. Imagine standing 100 kilometers away and seeing a pillar of darkness rising into the sky. So tall, it seems to pierce the heavens themselves. Imagine the sound, not a single explosion, but a continuous, earth-shaking thunder that goes on for hours, for days. The ash column spread outward in the upper atmosphere, carried by high-altitude winds. It drifted east across the Sea of Japan, falling like toxic snow on coastal villages. It drifted south, dusting the Korean peninsula in gray. Some particles, the finest ones, circled the entire Northern Hemisphere, creating blood-red sunsets as far away as Europe. Then came the pyroclastic flows. These are among the most lethal phenomena in nature. They are avalanches of superheated gas and pulverized rock that race down volcanic slopes at speeds exceeding 200 kilometers per hour. Nothing survives in their path. Not trees, not stone structures, not flesh. The flows from Paektu swept down the mountain's flanks in every direction, incinerating forests, filling valleys with deposits of ash and pumice that would remain hot for months afterward. The landscape was transformed into something lunar gray, lifeless, silent, and then the summit collapsed. When a volcano expels such enormous quantities of magma, it creates a void beneath the surface. The mountain above, no longer supported, simply falls inward. The collapse happened rapidly, perhaps in minutes, creating the immense caldera we see today. The sound of that collapse must have been heard hundreds of kilometers away. The ground shook as if the earth itself were breaking apart. And, in a sense, it was. Contemporary records from Japan mentioned strange atmospheric phenomena around this time. Chronicles speak of unusual fogs, of seasons that seemed out of balance, of harvests that failed. They did not know the cause. They could not have known that a mountain 1,000 kilometers away had just rewritten the geography of Northeast Asia. The Millennium Eruption of Mount Paektu was rated as a V6 or possibly V7 on the Volcanic Explosivity Index, a scale that measures the magnitude of eruptions. To reach V7 requires the ejection of at least 100 cubic kilometers of material. Paektu achieved this threshold, placing it among the most powerful eruptions of the Common Era. Only a handful of eruptions in recorded history match this scale. Tambora in 1815, which caused the year without a summer and global famine. The eruption of Santorini around 1600 BC, which may have contributed to the collapse of the Minoan civilization. These are events that alter not just landscapes, but the course of human history. Yet here is what makes Paektu's story particularly profound. Despite its extraordinary violence, despite the reshaping of an entire mountain range, the volcano did not end. It merely paused. Over the centuries that followed the Millennium Eruption, water slowly filled the caldera, rain fell, snow accumulated and melted each spring. Underground springs contributed their flow. Heaven Lake was born, a body of water cradled in the arms of catastrophe, serene and beautiful, as if the mountain were offering an apology for its rage. But beneath that tranquil surface, the magma chamber remains. The subduction continues. The Pacific Plate still descends into the mantle, still feeds the reservoir of molten rock below. The mountain has not spoken with such violence for more than a millennium. But it has not fallen silent either. In 1702, historical records document another eruption, smaller but significant. In 1903, there are reports of renewed activity. These were not continent-altering events. They were reminders, punctuation marks in a longer sentence. The Earth is patient. But the Earth also remembers what it is capable of. And so we come to the question that geologists ask today, the question that keeps them watching Paektu with instruments and satellites and seismographs. What happens next? There is a particular quality to volcanic silence that those who study such things come to recognize. It is not the silence of absence. It is the silence of anticipation, the silence of a held breath. For more than a century now, Mount Paektu has maintained this peculiar quiet. No dramatic eruptions, no columns of ash darkening the sky. To the casual observer, to the thousands who visit Heaven Lake each year during the brief summer months, the mountain appears dormant, peaceful, perhaps even dead. But those who listen carefully, who place sensitive instruments into the ground, who measure the chemistry of hot springs, who track the smallest tremors, know otherwise. The mountain is dreaming, and in its dreams, it stirs. In the early years of the 21st century, something changed. Between 2002 and 2005, seismologists detected an unusual increase in earthquake activity beneath Paektu. These were not dramatic quakes. Most registered below magnitude, for many were so subtle that only instruments could detect them. But their frequency was significant. Hundreds of small earthquakes in a region that had been relatively quiet for decades. To a volcanologist, this pattern has a name. It is called an earthquake swarm, and it often means one thing. Magma is moving. Deep beneath the mountain, molten rock was rising. Slowly, incrementally, it was finding pathways through the solid rock, exploiting weaknesses, creating new fractures. With each movement, the surrounding rock adjusted, cracked, settled. Each adjustment produced a tremor. At the same time, satellite measurements detected something equally concerning. The ground around the caldera was rising. Not dramatically, perhaps 10 centimeters over the course of several years, but, in geological terms, this was rapid. This was meaningful. The Earth was swelling. Like a blister forming on skin, like water heating in a sealed container, pressure was building beneath Paektu's surface. Scientists scrambled to install more monitoring equipment. Seismometers were placed at strategic points around the mountain. GPS stations tracked ground deformation with millimeter precision. Gas sensors analyzed the composition of emissions from fumaroles and hot springs, searching for changes in sulfur dioxide or carbon dioxide levels that might indicate rising magma. What they found was unsettling, but not yet alarming. The mountain was indeed awakening from its long slumber. But awakening does not necessarily mean eruption. Volcanoes can experience periods of unrest that last for years, even decades, without culminating in an eruption. The challenge, the maddening, humbling challenge that volcanologists face is that each volcano behaves differently. There is no universal timeline, no reliable script. Some volcanoes give months of warning before erupting. Others give hours. Some swell and tremble and then simply settle back into quietude, like a sleeper who shifts position but does not wake. By 2007, the seismic activity beneath Paektu began to decline. The ground deformation slowed, then stopped. The mountain, it seemed, had decided not to erupt. The magma that had risen found some equilibrium, some temporary resting place in the complex plumbing beneath the caldera. The immediate crisis passed, but the episode left scientists with a profound realization. Paektu was not the sleeping giant they had assumed. It was active, it was capable. And given its history, given the catastrophic power it had demonstrated in 946, the stakes of misreading its signals were extraordinarily high. Consider the geography. Mount Paektu sits on the border between China and North Korea, but its potential reach extends far beyond. Within 100 kilometers of the volcano live millions of people. Cities, towns, agricultural regions that feed even more millions. The Chinese city of Yanji, home to more than 500,000 people, lies just 80 kilometers from the summit. To the east, across relatively flat terrain, the ash and pyroclastic flows from a major eruption could reach well into northeastern China. To the south, prevailing winds would carry ash over the Korean peninsula both north and south. Seoul, with its metropolitan population of 25 million, lies approximately 500 kilometers away, far enough to avoid direct devastation, but close enough to suffer significant ashfall that could paralyze infrastructure, contaminate water supplies, collapse roofs. And then there is the aviation concern. Northeast Asia is one of the world's busiest air traffic corridors. Hundreds of commercial flights pass through this region daily, carrying passengers between China, Japan, Korea, and beyond. Volcanic ash is catastrophic for jet engines. It melts in the heat of the turbines, then solidifies, choking the machinery. Planes have fallen from the sky because of encounters with ash clouds. A major eruption at Paektu would shut down air traffic across the region for days, possibly weeks. The economic impact alone would measure in the billions. Yet despite these risks, monitoring of Paektu remains complicated by geopolitics. North Korea is among the world's most isolated nations. Scientific collaboration across its borders is limited. While Chinese scientists have access to the mountain's northern slopes, and while some international cooperation exists, the full picture of what is happening beneath Paektu remains frustratingly incomplete. It is as if we are trying to understand a conversation while hearing only every third word. We know something is being said. We can detect the tone, the emotional content, but the precise meaning eludes us. This is the reality of modern volcanology. For all our technology, for all our satellites and sensors and computer models, we are still, in many ways, at the mercy of the Earth's opacity. We can measure symptoms, we can detect patterns, but predicting the exact moment when a volcano will erupt, particularly a volcano as complex and powerful as Paektu, remains beyond our capabilities. What we can say with certainty is this: the magma chamber beneath Mount Paektu is not empty, it is not inactive. The forces that drove the Millennium Eruption have not disappeared. They have merely been waiting through dynasties and revolutions, waiting through wars and treaties, waiting through the rise of cities and the drawing of borders, waiting with the patience that only geological time can teach. And in that waiting, there is a question that hangs over the region like the mountain's shadow. Not if Paektu will erupt again, but when. The mountain keeps its own counsel. It answers to pressures and processes that operate on timescales we struggle to comprehend. 1,000 years is nothing to a volcano. It is barely a pause, barely a breath between sentences. Those who study Paektu do so with a mixture of fascination and humility. They know they are watching something immense, something with the power to reshape landscapes and alter climates. They know that somewhere beneath that beautiful, deceptive lake, the Earth is still composing its next statement. And they know that when that statement comes, we will have little choice but to listen. Heaven Lake holds 14 billion cubic meters of water. Let that number settle for a moment. 14 billion cubic meters. It is a volume almost impossible to visualize. Enough water to fill nearly 6 million Olympic swimming pools. Enough to submerge entire cities. And all of it rests in a bowl carved by catastrophe, perched more than 2,000 meters above sea level. The lake is beautiful beyond words. In summer, when the ice finally melts, its surface reflects the sky with such clarity that it becomes difficult to distinguish where water ends and heaven begins. Perhaps this is why the Koreans named it Changi Heaven Lake. Perhaps they sensed that this was a place where elements merged, where boundaries dissolved. But there is another reason scientists watch this lake with particular attention. Water and volcanoes are a dangerous combination. When magma rises beneath a body of water, especially a body of water this large, the potential for catastrophe multiplies exponentially. The interaction between molten rock and water creates what volcanologists call phreatomagmatic eruptions, driven not just by volcanic gases, but by the violent conversion of water into superheated steam. Imagine a single drop of water falling onto a red-hot surface. The instant vaporization, the explosive hiss. Now multiply that by billions upon billions of liters. The result is not merely an eruption. It is a detonation. The Millennium Eruption of 946 occurred before Heaven Lake existed, or when the lake was far smaller. The caldera was created by that eruption, and only afterward did water begin to accumulate. But if Paektu were to erupt again with similar force today, the presence of the lake would fundamentally alter the character of the event. The initial contact between rising magma and lake water could trigger massive steam explosions. The lake itself could be ejected into the atmosphere, billions of tons of water hurled skyward, then falling back as scalding rain across the surrounding region. Lahar's volcanic mud flows could race down the mountain's slopes at terrifying speeds, picking up ash and rock and debris as they descended, transforming into rivers of liquid concrete that bury everything in their path. This is not speculation. This is physics. This is what happens when you combine extreme heat with vast quantities of water in a confined space. In 1883, when Krakatoa erupted in Indonesia, Much of its destructive power came from the interaction between magma and seawater. The explosions were heard 3,000 miles away. The tsunamis generated by the eruption killed more than 36,000 people. Krakatoa's caldera was smaller than Paektu's. The body of water involved was the ocean. Not a mountain lake, but the principle remains the same. Water amplifies volcanic violence in ways that are difficult to overstate. And yet, paradoxically, the lake also serves as a kind of pressure relief valve. The weight of all that water, billions of tons pressing down on the caldera floor, helps to keep the underlying magma chamber sealed. It is a lid, heavy and cold, resisting the upward push of molten rock. This creates a delicate equilibrium. As long as the weight of the water exceeds the pressure of the magma below, the system remains stable. But if the magma pressure increases beyond a certain threshold, if enough molten rock accumulates and rises, the balance tips. What concerns scientists most is not necessarily a repeat of the Millennium Eruption, though that possibility cannot be dismissed. What concerns them is the unpredictability introduced by the lake. A smaller eruption, one that might ordinarily be manageable, that might produce localized damage but not regional catastrophe, could be transformed by the water into something far more dangerous. The lake could drain catastrophically, sending a wall of water and volcanic debris down the mountain. It could be ejected as superheated steam, creating pyroclastic surges that travel even faster and farther than normal. The scenarios multiply, each more complex than the last, each dependent on variables that cannot be precisely measured or predicted. Chinese geologists have studied the caldera structure intensively. They have mapped the lake floor using sonar. They have measured water temperature at various depths, searching for thermal anomalies that might indicate hotspots where magma approaches closer to the surface. They have drilled cores from the lake sediments, reading the layers like pages in a book, searching for evidence of past eruptions that might have gone unrecorded by human observers. What they have found is sobering. The sediment record suggests that even during the centuries after the Millennium Eruption, when historical records are sparse or non-existent, the volcano experienced episodes of activity, small eruptions, perhaps, or submarine venting of gases and heat. Events that disturbed the lake but did not destroy it. The mountain, in other words, has never been truly dormant. It has merely been cycling through periods of greater and lesser activity, like a heart beating with irregular rhythm. There is something profoundly humbling about standing at the edge of Heaven Lake, and many have stood there. Scientists and pilgrims alike, and contemplating what lies beneath. The water is so clear, so blue, so serene. Birds circle overhead. The wind whispers through the volcanic rock. It all seems so permanent, so stable. But permanence is an illusion we impose on landscapes. The earth knows nothing of permanence. It knows only transformation. The rock beneath your feet was once magma. The lake that seems so ancient is barely 1,000 years old, younger than many of the world's great cathedrals. The caldera that cradles the water was created in a span of time shorter than a human lifetime. Everything here is transient. Everything here is in the middle of a story that has not yet concluded. For the people who live within sight of the mountain, this knowledge exists in layers. There is the everyday knowledge that the mountain is there, has always been there, will always be there. This is the knowledge of farming seasons and weather patterns, of where to graze livestock and when to harvest crops. And then there is the deeper knowledge, passed down through generations, embedded in myths and legends. The knowledge that the mountain is sacred precisely because it is powerful. That it must be respected not merely as a symbol, but as a living force. The shamans of old Korea understood this, even if they lacked the scientific vocabulary to express it. They knew that mountains could breathe fire. They knew that the earth could open and swallow the unwary. They approached Paektu with reverence and caution, understanding that they were in the presence of something vastly greater than themselves. Modern science has given us new language, new tools, new ways of measuring and predicting. But it has not fundamentally changed the relationship. We are still small creatures standing before immense forces. We are still trying to read the intentions of a planet that operates according to rules we only partially understand. Heaven Lake remains beautiful. Heaven Lake remains deadly. These two facts are not contradictory. They are complementary. They are two aspects of the same truth. The mountain will speak again. The water will play its role in that conversation. And when the time comes, we will witness once more what our ancestors witnessed in 946, the moment when the earth reminds us that we are guests here, temporary residents on a restless planet. Until then, the lake dreams beneath the sky, holding its secrets close, waiting for the moment when silence transforms into thunder. There is an art to listening to mountains. It requires instruments sensitive enough to detect vibrations smaller than the width of an atom. It requires patience to parse patterns from noise, signal from static. It requires the humility to accept that even with all our technology, the Earth will always know more than we do. At various points around Mount Paektu, seismometers rest in carefully chosen locations. Some are buried in shallow pits to shield them from wind and temperature fluctuations. Others sit in small concrete bunkers, protected from the elements. Each one listens constantly, recording every tremor, every shift, every whisper from the deep. The data flows back to monitoring stations, where scientists review it daily, searching for patterns that might indicate change. They are looking for specific signatures, the kinds of earthquakes that suggest magma movement rather than ordinary tectonic adjustment. There are earthquakes caused by rock fracturing under stress. These produce sharp, high-frequency signals, sudden cracks in rigid stone. Then there are earthquakes caused by fluid movement, by magma or superheated water forcing its way through fractures. These produce longer, lower-frequency signals, sustained rumble rather than a sharp snap. The difference is subtle but crucial. It is the difference between hearing a branch break and hearing water flowing through pipes. Both make sound. Both indicate movement. But they tell entirely different stories about what is happening underground. Between 2002 and 2005, when Paektu experienced its most recent significant unrest, the seismometers recorded predominantly the second type of signal. The earthquakes were not brittle fractures, they were something was moving beneath the mountain, and that something was almost certainly magma. But seismology alone cannot tell the complete story. Scientists also monitor ground deformation, the subtle swelling or subsiding of the Earth's surface as magma chambers fill or empty, as pressure increases or decreases. GPS stations around the caldera track position with extraordinary precision. They can detect vertical movement of just a few millimeters, horizontal shifts of even less. During the 2002 to 2005 unrest, these stations recorded uplift. The ground was rising, dome-like, centered roughly beneath the caldera. The pattern was consistent with magma intrusion at shallow depth, perhaps 5 to 10 kilometers below the surface. For reference, the Earth's crust in this region extends down approximately 30 to 40 kilometers before meeting the mantle. So this magma was not rising from the deepest reservoirs. It was relatively near the surface. Geologically speaking, it was practically knocking at the door. Then there are the gases. Volcanoes breathe. Even when they are not erupting, they release gases through fumaroles, through hot springs, through soil pores invisible to the naked eye. These gases come from deep sources, from magma itself, from heated groundwater, from chemical reactions occurring at high temperature and pressure. Scientists collect gas samples from around Paektu and analyze their composition. They are particularly interested in three gases: carbon dioxide, sulfur dioxide, and helium. Carbon dioxide can come from many sources, but certain isotopic signatures indicate a deep origin, a magmatic source. Sulfur dioxide is even more telling. It comes almost exclusively from magma, from dissolved gases being released as molten rock rises and pressure decreases. A sudden increase in sulfur dioxide emissions often precedes eruptions. Helium isotopes provide another piece of the puzzle. Helium-3, a rare isotope, comes primarily from the mantle. Its presence in volcanic gases indicates that material from very deep sources, deeper than the crust, is making its way toward the surface. During the early 2000s unrest, gas measurements around Paektu showed increases in all three of these indicators. The mountain was not just experiencing shallow disturbances, it was receiving fresh input from deep reservoirs. The magmatic system was active, connected, alive. Stories like this are not meant to be rushed. They are meant to be followed by those who still listen. If this journey resonates with you, you are already part of Fury of the Earth. What makes volcano monitoring both fascinating and frustrating is that these signals, seismic deformation, gas emissions, do not always correlate neatly. Sometimes earthquakes increase without any ground deformation. Sometimes the ground swells without significant gas release. Each volcano has its own personality, its own way of expressing internal changes. Paektu's behavior in the early 2000s suggested a classic magmatic intrusion. But the intrusion did not culminate in eruption. Instead, the activity gradually subsided. By 2010, seismicity had returned to background levels. Ground deformation had stabilized. Gas emissions remained elevated compared to pre-2002 levels, but not dramatically so. What happened? Where did the magma go? The most likely explanation is that it stalled. As magma rises, it seeks pathways of least resistance. Sometimes it finds them and continues upward. Sometimes it encounters barriers, layers of particularly strong rock, or zones where the surrounding pressure is too great and it simply stops. It pools at that depth, cooling slowly, crystallizing, becoming part of the solid crust. This is not failure. This is simply the normal behavior of magmatic systems. For every eruption that reaches the surface, there are dozens of intrusions that do not. The Earth is filled with these frozen remnants of almost eruptions, solidified magma that never quite made it to daylight. But here is what concerns scientists. The magma that rose between 2002 and 2005 did not disappear. It added to the existing reservoir. It increased the total volume of molten rock somewhere beneath the mountain. And the system that produced that intrusion, the subduction of the Pacific plate, the melting of rock in the mantle, the transport of magma upward is still operating. The next intrusion could happen next year, or next decade, or next century. But given the mountain's history, given the evidence of ongoing magmatic activity, there will be a next time. International collaboration in monitoring Paektu has improved somewhat in recent years. Chinese institutions have published more of their data. South Korean scientists, though unable to access the mountain directly, contribute through satellite analysis and regional seismic networks. Even North Korea has occasionally allowed limited scientific exchange. Recognizing that volcanic threats do not respect political boundaries, but significant gaps remain. The density of monitoring instruments is far lower than at better studied volcanoes, like Vesuvius or Mount Fuji. Large areas of the mountain, particularly on the North Korean side, have no real-time monitoring at all. We are watching Paektu, but not as closely as we should be given its potential for catastrophe. It is like having a guard outside a fortress who can hear sounds from within but cannot see through the walls. He knows something is happening. He can make educated guesses, but he cannot be certain. This is the reality for volcanologists working on Paektu today. They have tools their predecessors could only dream of. They can detect movements and changes that would have been completely invisible a century ago. Yet they are still fundamentally limited by the opacity of rock, by the complexity of magmatic systems, by the vastness of the forces at play. The mountain keeps its counsel, and we keep listening, knowing that someday, perhaps tomorrow, perhaps in 100 years, the signals will change, the patterns will shift, and we will have to interpret them quickly and correctly, because lives will depend on getting the warning right. When Mount Tambora erupted in Indonesia in April of 1815, the world did not yet understand what had happened. In the days and weeks following the eruption, ash fell across the Indonesian archipelago. Ships at sea, hundreds of miles away, found their decks coated in grey powder. The sky darkened. The sun appeared as a dim red disk through the haze, when it could be seen at all. But the full consequences took months to unfold. The eruption had injected enormous quantities of sulfur dioxide into the stratosphere, the upper layer of atmosphere where weather does not reach, where particles can linger for years. These sulfur compounds formed tiny droplets of sulfuric acid suspended in the air, creating a veil around the entire planet. The veil reflected sunlight back into space. Less solar energy reached the Earth's surface. Global temperatures dropped. The year 1816 became known as the year without a summer. Snow fell in June across New England. Crops failed throughout Europe. Famine spread. People starved in numbers that historians still debate, but which certainly reached into the hundreds of thousands, and they did not know why. They could not connect the cold summer in London to a mountain that had exploded on the other side of the world. They lacked the scientific framework to understand that atmosphere connects all places, that what happens in one location can affect the entire planet. Mount Paektu's Millennium Eruption in 946 was comparable in scale to Tambora, perhaps even larger. The volume of material ejected was similar, more than 100 cubic kilometers. The height of the eruption column was likely comparable. The amount of sulfur dioxide released would have been immense. What this means is that Paektu did not merely affect Northeast Asia. It affected the climate of the entire Northern Hemisphere. Ice cores drilled from Greenland preserve a record of past atmospheric conditions. Each year of snowfall leaves a layer, and within those layers, scientists can detect traces of volcanic sulfur. The ice cores from around the year 946 show a significant sulfur spike, evidence of a major volcanic event somewhere in the Northern Hemisphere. For years, scientists debated which volcano was responsible. Some suspected Iceland, others looked to Alaska. But eventually, through careful geochemical analysis matching the sulfur composition to known volcanic sources, they identified Paektu as the culprit. The eruption would have created spectacular sunsets for months afterward. The suspended particles scatter light in particular ways, painting the sky in deep reds and purples. Artists in Europe and the Middle East may have witnessed these displays without understanding their cause. More significantly, the eruption would have cooled global temperatures by perhaps 0.5 degrees Celsius for several years. This might not sound dramatic, but in agricultural societies operating at the margins of survival, even small temperature changes could mean the difference between adequate harvest and famine. Historical records from this period are fragmentary. The year 946 fell during transitions and upheavals across multiple civilizations. In Korea, The later Three Kingdoms period was giving way to the unified Goryeo dynasty. In China, political fragmentation preceded the Song dynasty's consolidation of power. In Europe, the medieval period was deepening. Could climate disruption from Paektu have played a role in these transitions? Could harvest failures have contributed to political instability? These are questions we can ask but cannot definitively answer. History is too complex, too multi-causal, to draw simple lines between volcanic eruptions and human events. But we do know this: large eruptions matter beyond their immediate vicinity. They inject particles and gases into a shared atmosphere that belongs to no nation, that recognizes no borders. What rises from a mountain in Korea can fall as acid rain in Japan, can alter temperatures in China, can affect monsoon patterns across Asia. This is why modern scientists monitor not just the seismic and deformation signals at Paektu, but also prepare atmospheric models for potential future eruptions. They run computer simulations asking, if Paektu erupts again with V6 or 7 magnitude, where will the ash cloud travel? How high will it reach? How long will it persist? The answers depend on many variables. The season of eruption matters enormously. Winter and summer wind patterns in Northeast Asia differ significantly. An eruption in January would send ash in different directions than one in July. The height of the eruption column also matters. Ash that reaches the stratosphere behaves differently than ash confined to the troposphere. But some conclusions are consistent across models. A major eruption at Paektu would disrupt air traffic across a vast region. Tokyo, Beijing, Seoul, Shanghai, major aviation hubs would likely face temporary closures. The economic cost would be measured not in millions but in billions of dollars per day. Agricultural impacts would vary by distance and wind direction. Areas receiving heavy ashfall would face crop damage, contaminated water supplies, infrastructure damage. Roofs collapse under the weight of accumulated ash. Machinery fails as abrasive particles infiltrate engines and electronics. But perhaps the most insidious effect is the one that operates at a planetary scale. If Paektu were to inject sufficient sulfur dioxide into the stratosphere and a V7 eruption, almost certainly global cooling would follow. Not dramatically, not enough to plunge the world into ice age conditions, but enough to stress agricultural systems already challenged by climate change and population growth. We live in a more interconnected world than existed in 946 or 1815. Global food supplies depend on complex supply chains. Just-in-time inventory systems mean there are fewer reserves, less buffer against disruption. A significant volcanic eruption in one region can create ripple effects that touch lives everywhere. This is not meant to incite fear. It is meant to cultivate understanding. Volcanoes are not merely local phenomena. They are part of Earth's global systems, geological, atmospheric, ecological. They remind us that we live on a dynamic planet where forces beyond our control continue to shape conditions for all life. Scientists who study volcanic impacts on climate do so with a mix of fascination and concern. They are fascinated by the elegant complexity of Earth's systems, how energy from the sun, filtered through volcanic particles, affects temperature, which affects weather, which affects growing seasons, which affects human societies. They are concerned because they understand the stakes. A major eruption at a volcano like Paektu would be manageable in the sense that civilization would not collapse, but it would cause suffering, disruption, economic loss, perhaps loss of life. The goal of monitoring is not to prevent eruptions. We cannot do that. The goal is to understand them well enough to provide warning, to enable preparation, to give people time to move away from the most dangerous zones. This requires international cooperation at a level that often seems difficult to achieve. Volcanic monitoring data needs to be shared freely across borders. Hazard maps need to be created and updated. Evacuation plans need to be tested. Early warning systems need to be installed. At Paektu, these efforts are ongoing but incomplete. Progress is made, then stalls. Political tensions interfere. Resources are limited. And always, there is the question, how much do you invest in preparing for an event that might not happen for decades or centuries? It is a question without easy answer. But history offers guidance. The cost of preparation is always less than the cost of being unprepared. Always. The ash from Tambora circled the world in 1815, teaching humanity a lesson about interconnectedness that many did not fully grasp at the time. The ash from Paektu circled the world in 946, leaving its signature in ice core that would not be read for another 1,000 years. When Paektu erupts again the ash will rise once more into an atmosphere that connects us all, and we will learn, once again, that we are passengers on a restless planet, subject to forces far greater than ourselves. There are approximately 3 million people living within 100 kilometers of Mount Paektu's summit. 3 million lives. 3 million stories. Farmers tending fields that their families have worked for generations. Children attending schools in towns with names most of the world has never heard. Elderly people who have watched the mountain through every season of their long lives, who know its moods the way one knows the face of an old friend. These are not statistics. These are people whose existence is woven into the landscape, for whom the mountain is not an abstraction or a scientific curiosity, but simply part of the world they inhabit. To the west, in China's Jilin province, cities like Yanji and Beishan have grown steadily over recent decades. Modern apartment blocks rise alongside older structures. Markets bustle. Factories operate. Life proceeds with the assumption of continuity, that all communities share the belief that tomorrow will essentially resemble today. On the Korean side, communities are smaller, more dispersed, but no less rooted in place. The mountain holds profound cultural significance here. It appears in the national narrative, in founding myths, in collective memory. To suggest evacuation from this region would not merely be a logistical challenge. It would be asking people to abandon something fundamental to their identity. This is the human dimension of volcanic risk, and it is perhaps the most complex aspect of all. Scientists can model eruption scenarios. They can calculate pyroclastic flow distances, ash dispersal patterns, lahar. They can produce maps showing zones of different hazard levels, color-coded from red to yellow to green. But maps cannot capture what it means to tell someone their home sits in the red zone. Maps cannot convey the weight of deciding whether to evacuate a city based on signals that might indicate an imminent eruption, or might simply be another episode of unrest that subsides without culmination. Volcanology, at its heart, is not just a physical science. It is a human science. The challenge is compounded by the nature of volcanic precursors. Unlike earthquakes, which strike with little warning, volcanic eruptions often announce themselves days, weeks, sometimes months in advance. Seismic activity increases. Ground deformation accelerates. Gas emissions intensify. These are the volcano's warnings. But they are not guarantees. A volcano can show all the signs of imminent eruption and then simply stop. The magma stalls. The system stabilizes. The crisis passes. This creates an agonizing dilemma for authorities. Order an evacuation too early, based on ambiguous signals, and you disrupt millions of lives unnecessarily. You damage your credibility for future warnings. You cause economic harm, that may never be recovered. Wait too long, hoping for clearer signals, and you risk catastrophe. You risk being the official who failed to act, whose caution became complicity in disaster. There is no perfect answer to this dilemma. There is only the attempt to balance probabilities against consequences, to make decisions with incomplete information under pressure of time. Other volcanic regions offer instructive examples. Mount Pinatubo in the Philippines erupted in 1991 after decades of dormancy. Fortunately, monitoring equipment had been installed, and scientists recognized the escalating signals. Evacuations were ordered. Tens of thousands of people were moved away from the danger zones. The evacuation was chaotic. People resisted leaving their homes. Livestock could not all be transported. Possessions had to be abandoned. But when Pinatubo erupted with V6 magnitude comparable to Paektu's Millennium Eruption, the death toll was measured in hundreds rather than tens of thousands. The evacuation, despite its difficulties, saved an enormous number of lives. Contrast this with Nevado del Ruiz in Colombia in 1985. Scientists detected warning signs. They issued alerts, but communication failures, bureaucratic delays, and public skepticism meant that evacuations were not carried out. When the eruption triggered massive lahars that swept down river valleys, the town of Amaro was buried. More than 20,000 people died. These case studies are studied intensively in volcanology courses. They are cautionary tales, but also instructive ones. They teach that monitoring alone is not enough. You need communication systems. You need public trust. You need plans that people understand and accept. At Paektu, the groundwork for such systems is incomplete. Monitoring exists but could be better. Communication channels between scientific institutions and civil authorities function but are not seamless. Public education about volcanic hazards is limited in some areas, more developed in others. And there is the geopolitical complexity. An eruption at Paektu would affect multiple nations. Ash would not respect borders. Lahars might flow into both Chinese and Korean territory. Refugees might seek shelter across international boundaries. Coordination of emergency response across these borders would require levels of cooperation that do not currently exist. It would require trust, shared protocols, advance agreements about everything from evacuation routes to refugee accommodation to post-disaster recovery. These are not insurmountable challenges, but they are real ones, and they exist in tension with the simple fact that the mountain operates according to its own timeline, indifferent to human politics. There is also the question of what happens after. Eruptions do not just destroy, they transform. Volcanic ash, once it settles and weathers, becomes extraordinarily fertile soil. Some of the world's most productive agricultural regions sit on volcanic deposits. Indonesia, with its dense population, occupies a volcanic archipelago precisely because the soil yields abundant harvests. The people living around Paektu understand this in their bones. They understand that the mountain gives as well as takes. The hot springs that bubble from volcanic heat attract visitors, generate income. The dramatic landscape draws tourists. The mineral-rich soil supports agriculture. This is why communities persist in volcanic zones despite the risks. It is not ignorance. It is a calculated acceptance of trade-offs. The benefits, most years, outweigh the dangers. Life near a volcano is like life in earthquake zones, hurricane regions, floodplains. It is accepting that nature occasionally demands a reckoning, but that between those reckonings there is beauty and bounty. What has changed is our ability to see the reckonings coming. We are no longer completely at the mercy of surprise. We have tools, knowledge, systems. They are imperfect. They will always be imperfect, but they give us a chance. The 3 million people within Paektu's reach do not spend their days in fear. They cannot. Life requires a certain bracketing of existential risk, a focus on the immediate and the manageable. You plant crops, you send children to school, you plan for next year, next decade, but somewhere in the background, for those who think about such things, there is awareness. The mountain is there. It has spoken before. It will speak again. And when it does, we will discover whether our preparations were adequate, whether our warnings were heeded, whether we managed to balance the scales between human vulnerability and natural power. This is not a story with a resolution. It is a story still unfolding. The people and the mountain, sharing a landscape, sharing a future that neither can fully control. It is a relationship defined by respect, by adaptation, by the simple necessity of coexistence with forces vastly greater than ourselves. Every volcano is a library, written in its rocks, in the layers of ash and pumice and hardened lava, is a complete history of its behavior. Each eruption leaves a signature. Each quiet period leaves a gap. Together, they form a chronicle more reliable than any human record. Because stone does not forget and stone does not embellish. Scientists who study Mount Paektu are not only watching the present, they are reading the past. Around the mountain, in valleys and on slopes, lie deposits from eruptions that occurred long before humans kept written records. These deposits can be mapped, sampled, dated. They reveal patterns that would otherwise remain hidden. The technique is called tephrochronology, the study of volcanic ash layers through time. Each eruption produces ash with a unique chemical fingerprint, a specific composition of minerals and glass that reflects the exact conditions in the magma chamber at that moment. By analyzing these fingerprints, scientists can match ash deposits found in different locations back to their source, eruption. Ash from Paektu's Millennium Eruption has been found in lake sediments across northern Japan, in peat bogs in Korea, in marine core from the Sea of Japan. Each discovery adds detail to the reconstruction of what happened in 946. The distribution pattern tells us about wind direction and intensity at different altitudes. But the Millennium Eruption, dramatic as it was, represents only one chapter in a much longer story. Deeper excavations, looking at older layers, reveal that Paektu has been active for hundreds of thousands of years. The mountain we see today is actually the latest iteration in a long succession of volcanic edifices that have grown, erupted, collapsed, and regrown on this same spot. Approximately 500,000 years ago, volcanic activity began in this region as the subduction zone beneath became established. Over time, a stratovolcano built itself through countless eruptions, layers upon layers of lava and ash accumulating, growing taller with each episode. There were likely multiple major collapses before the one in 946. Each time the magma chamber emptied catastrophically, the summit would fall inward, creating a caldera. Then, over subsequent millennia, new eruptions would partially fill that caldera, building a new cone, starting the cycle again. This is the nature of large volcanic systems. They are not permanent structures. They are temporary accumulations, constantly being built up by eruptions and torn down by collapses. The mountain we call Paektu is simply the current phase in this ongoing construction and destruction. Geologists can trace at least 3 major caldera-forming events in Paektu's history before the Millennium Eruption. The oldest, most degraded calderas are visible only in subtle topographic features and in the geometry of ancient deposits. But they are there, if you know how to read the landscape. This long-term perspective is crucial. It tells us that massive eruptions at Paektu are not anomalies. They are the volcano's normal mode of behavior. Every few tens of thousands of years, sometimes more frequently, the system builds toward a climactic eruption that reshapes the entire edifice. The Millennium Eruption is simply the most recent in this series, and from a geological perspective, it was not that long ago. 1,000 years is barely a moment in volcanic timescales. When scientists look at the deposits from smaller, more recent eruptions, the ones from 1702, from 1903, from various undated events recorded only in the rock, they see a volcano that remains active at a fundamental level. These smaller eruptions are not separate phenomena. They are part of the same ongoing magmatic system, the same deep, source-feeding molten rock upward. Between the major caldera-forming eruptions, Paektu experiences centuries of lesser activity. Small explosions, lava flows that don't travel far. Phreatic eruptions where groundwater flashes to steam without involving fresh magma. These are the volcano's ordinary vocabulary, the routine conversation it maintains with the surface. One of the most valuable archives exists in the sediments beneath Heaven Lake itself. Core samples drilled from the lake floor contain layers that record every significant event since the lake formed. Some layers are fine clay deposited during quiet periods. Others are coarse ash from explosive eruptions. Some show evidence of underwater landslides triggered by earthquakes. Reading these cores is like reading tree rings, but instead of recording climate, they record volcanic activity. Scientists can count back through the layers, dating them using various techniques, reconstructing a timeline of the volcano's behavior over the past millennium. What they find is sobering. Even during the historical period, when we might expect human records to capture major events, there are eruption deposits in the lake sediments that correspond to no known written accounts. Either the records were lost, or the eruptions occurred during periods when human presence in the region was minimal, or the events were witnessed but not considered significant enough to document. This suggests that our historical record of Paektu's activity is incomplete. We know about the Millennium Eruption because it was impossible to ignore. We have scattered references to later events, but there may be eruptions that occurred and were simply forgotten. The stone remembers what humans forget. There is also the evidence from comparison with other volcanoes. Paektu is not unique. It is part of a broader category of large caldera systems that includes Yellowstone in the United States, Taupo in New Zealand, Toba in Indonesia. These are volcanoes capable of supereruptions, vents that occur rarely but have global consequences when they do. By studying the behavior of these other systems, scientists gain insight into how Paektu might behave. They see patterns, long periods of dormancy punctuated by brief periods of intense activity, cycles of magma accumulation and release that operate over timescales of tens of thousands of years. The challenge is that these patterns are not perfectly regular. You can not simply calculate when the next major eruption will occur based on the intervals between past eruptions. Volcanic systems are too complex, too influenced by variables we cannot fully measure. The accumulation rate of magma varies. The strength of the rock confining the magma chamber changes. External factors like regional tectonic stress play roles we are only beginning to understand. What the archive of stone can tell us is the range of possibilities. It tells us that Paektu is capable of V7 eruptions. We know this because it has produced them. It tells us that smaller eruptions occur more frequently. The deposits prove this. It tells us that the system operates continuously, that periods of surface quiet do not mean cessation of deep activity. Armed with this knowledge, Scientists can make informed assessments of risk. They cannot predict when the next eruption will occur, but they can say with confidence that it will occur. They can describe what forms it might take based on past behavior. They can identify the warning signs that should prompt escalated monitoring and preparation. The archive is still being written. Every year that passes without eruption is itself data. Every small earthquake, recorded by seismometers, adds to the record. Every gas measurement, every satellite image, every GPS reading contributes to our understanding. We are living through a chapter in Paektu's story. The chapter happens to be a relatively quiet one, punctuated by episodes of unrest, but not yet by eruption. How long this chapter will continue, no one can say with certainty. But the stone is patient. It has recorded hundreds of chapters before this one, and it will record hundreds more after we are gone, after our cities have crumbled, after our languages have been forgotten. The mountain will continue its ancient rhythm, building and collapsing and building again, indifferent to whether anyone is watching. We watch anyway, because that is what it means to be human, to study, to learn, to try to understand our place in a story far larger and longer than ourselves. There is a particular quality to standing at the edge of Heaven Lake in winter. The surface is frozen solid, a sheet of ice thick enough to walk upon. Snow covers everything in undifferentiated white. The wind moves across the caldera with nothing to slow it, carrying crystals of ice that sting exposed skin. The cold is profound, bone deep, the kind of cold that makes you understand how inhospitable this place can be. And yet, even in winter, steam rises from certain points around the shore. Hot springs continue to flow beneath the ice, creating patches of open water that never freeze. The heat from below persists regardless of season, regardless of surface temperature. This is what the mountain has been trying to tell us all along. That beneath the quiet, beneath the beauty, beneath the frozen surface, it remains active. It remains capable. It is not sleeping. It is waiting. We have followed this story through deep time and recent history. Through the catastrophic violence of 946 and the subtle unrest of the early 2000s. Through scientific monitoring and human habitation. Through the archive of stone and the complexity of prediction. Now we arrive at the question that has no answer but demands to be asked. What happens next? The honest response is that we do not know. We cannot know. The Earth operates according to rhythms that exceed our capacity for prediction. We can identify precursors. We can calculate probabilities. We can prepare response plans. But we cannot schedule volcanic eruptions the way we schedule appointments. What we can do is maintain vigilance. The seismometers will continue their patient listening, recording every tremor, every shift in the deep conversation between rock and magma. The GPS stations will continue tracking millimeter-scale movements of the surface. The gas sensors will continue sampling the volcano's breath. Satellites will continue photographing the mountain from orbit, measuring heat signatures, detecting changes invisible from the ground. All of this data flows into models, into analysis, into the collective understanding held by scientists who have dedicated their careers to comprehending this one mountain. They watch because the consequences of not watching are unacceptable. They watch because 3 million people live within the mountain's reach. They watch because we now possess the tools to see what previous generations could not. But there is a deeper reason to watch, one that transcends practical concerns about hazard and safety. We watch because the Earth is teaching us something fundamental about existence itself. It teaches us about impermanence. That mountains which seem eternal are actually transient. That landscapes change. That what appears solid is actually fluid when viewed across sufficient time. It teaches us about humility. that despite all our technology, all our scientific advancement, we remain small creatures, subject to forces vastly greater than ourselves, that we cannot control the planet we inhabit. We can only adapt to it. It teaches us about patience, that some processes cannot be rushed, cannot be abbreviated to fit human timescales, that understanding requires sustained attention across decades, across generations, and perhaps most importantly, it teaches us about connection, that an eruption on one mountain affects an entire hemisphere, that ash crosses borders without permission, that we share an atmosphere, a planet, a fate. Mount Paektu will erupt again. This is not pessimism. This is geology. The magma chamber continues to receive input from the mantle below. The tectonic forces that created this volcano continue to operate. The system remains fundamentally active. When the eruption comes, whether in our lifetimes or our children's lifetimes or centuries, from now it will be a moment of transformation. Landscapes will change. Lives will be disrupted. The mountain will demonstrate once again what it is capable of when the pressure becomes too great to contain. But it will also be a moment of revelation, of seeing with our own eyes or through the eyes of instruments the raw power of planetary processes, of witnessing what our ancestors witnessed in 946 when the sky darkened and the earth shook, of being reminded that we live on a world still in the process of forming itself, still molten at its core, still young by cosmic measures. The scientists will do their work. They will issue warnings based on the best available data. Authorities will make difficult decisions about evacuations and emergency responses. People will flee or shelter in place according to their circumstances and choices. And when it is over, when the ash settles and the lahars drain and the pyroclastic flows cool, the work of recovery will begin. Communities will rebuild. Fields will be cleared. Life will reassert itself the way it always does in volcanic landscapes, stubbornly, persistently, adapting to the new conditions. Eventually, decades later, the ash will weather into soil, vegetation will return. The scars will fade into the landscape's texture. And a new generation will grow up knowing the mountain only as it appears then, unable to fully imagine it as it appears now. This is the cycle. Destruction and renewal. Catastrophe and recovery. The Earth's ancient rhythm, playing out across timescales that dwarf individual human lives, but which, collectively, we are learning to comprehend. Heaven Lake will remain, unless the next eruption is large enough to drain it. The caldera will endure, perhaps deepened, perhaps partially filled with new deposits. The summit will be reshaped into whatever form the eruption dictates, but the mountain will persist, changed but recognizable, still sacred to those who consider it so, still geologically active, still breathing steam into cold air, still trembling occasionally with deep earthquakes, still participating in the grand conversation between the Earth's interior and its surface. We are privileged to live in an era when we can observe these processes with unprecedented clarity, when we can see beneath the surface, when we can measure the invisible, when we can connect events separated by vast distances and recognize them as part of a unified system. This knowledge brings responsibility. To share what we learn, to prepare those at risk, to approach the Earth with respect rather than arrogance. But it also brings wonder, the simple, profound wonder of understanding that we inhabit a living planet, that the ground beneath our feet is not static but dynamic, that mountains are not permanent monuments but temporary expressions of forces still at work. Mount Paektu stands at the border between nations, between past and future, between human time and geological time. It has stories yet to tell, eruptions yet to produce. lessons yet to teach. The planet will continue its ancient rhythm long after we are gone. Continents will drift. Mountains will rise and erode. Volcanoes will erupt and rebuild. The cycle will continue with or without observers, with or without those who care to understand. But we are here now. We are watching, we are listening. And in doing so, we join ourselves to something immeasurably larger than our individual lives. If you wish to keep walking beside these powerful forces, subscribe to Fury of the Earth, and join us in the next chapter of the planet's unfolding story. The mountain waits, the Earth remembers, and we, for this brief moment in time, stand witness to both.